Hello and welcome to my poster, presenting 10 tips for protein proper prediction using machine learning. There are several things that we've seen many people get wrong, for example, in submitted manuscripts, but also in published papers. And if we reread some of our own papers, then also we've not done things optimally in the past. We've been developing methods for protein property prediction, mainly protein interactions from sequence, but these tips also will hold for structure-based predictions and also for other types of prediction targets. My name is Anton Feenstra. I'm from the Vrije Universiteit in Amsterdam, and together with Chingzhen and Kati and Dea, we wrote this paper summarizing the things that we found over the years. And I'll walk you through them briefly. So first and foremost, you will want to have a biological question. This allows you to design your method appropriately, choose the one that works, and also interpret your results at the end. Then your data set needs to be clearly described. Where does your data come from? Which databases have you used? How have you integrated annotations from different sources? And which filtering steps have you used so that you can explain which proteins and which annotations finally end up in the data sets. Then a third one that's often overlooked by people with a computer science background or machine learning background, to watch out for sequence similarity mainly between your training set and your test set. If your training set has homologs that are close to your test set, then the test set is not independent. But also, if you have many sequences from certain protein families, then your training set is very biased towards those. Then also your features and also your prediction targets can be at different levels in the protein. They can be residue-based, they can be annotated on regions, but they can also be global features. So for example, protein length is clearly a global feature, interaction site is clearly a residue-based feature, but something like solvent accessibility or hydrophobicity can be specified both at global or at the local level, and this has to be clear. Now, if you're developing a method, then you eventually want to compare it to other methods, and you'll need evaluation metrics to compare that, something like specificity or sensitivity or F1 measure and so on. But it's occurred several times that we find a paper with a method that's interesting, but they only report F1 and MCC, and then another paper only reports AUC and specificity, and then you cannot compare them directly. So this is very easily solved. You write a script to calculate those metrics. You just calculate all of them. You put a relevant selection in your main text and all the others in your supplement. Now, something that we've actually also seen being specified and not clearly is where do you get your positives and negatives and how are they defined? So for example, again, a protein interaction site, but if you use structures from the PDB, did you use a distance cutoff or do you use buried surface area, and which cutoffs did you use for that? And then also, is a negative just everything else that's not positive? Or, for example, do you exclude the buried interior of the protein, and do you only distinguish surface residues that are not interfaced, that are going to be your negative set? In most method papers, you'll find multiple data sets that's used for training and also for testing, and also multiple methods being developed, maybe different architecture or something. If you then say at some point for the figure, these are the results for the model, it might not be clear which one you're referring to. So if you label your data sets and you label your different architectures and you label your test sets, then you can say, here's the result for architecture A, trained on data set B, and tested on test set C. And then it's all very clear and unambiguous. Then most people think of machine learning as mostly a black box. So we don't know how these models work, so we have to just trust their output. But you can actually really shine some light into this black box. The simplest one is to just look at distributions of your input features, but there is also different methods to determine feature importance So you can compare whether different features were important for different kinds of predictions. There's also more sophisticated methods like SHAP values that will allow you to do that even per individual prediction, like for a single residue, which were the features that contributed positively or negatively to this specific prediction. And then if you have this, you can actually try and interpret that back into the context of your biological question that you started out with. Now, I already mentioned comparison. You need metrics for that, but your comparison also should be fair. So that means ideally you want to have all the methods tested on the same test set. But also even there, if the test set is closer to some of the training sets for some methods, then they might have an unfair advantage compared to other methods. So it's usually a good idea to use several test sets and then look for consistency of performance for the different methods on several test sets. Preferably also include a new test set that you've just created out of like later submissions into the database, so that you have some data that none of the methods have seen. Sometimes we've seen that people have a structure-based method and then compare it to sequence-based methods. That's not entirely fair. Here I've actually done the opposite. I include one structure-based method just to see how far we can get in that context with the sequence-based methods. And then you see that actually the difference is quite surprisingly low, and we're not yet sure why that is. So if you want to discuss that, ask me at my poster. Finally, you want your method to be used, so make it available. Use a GitLab link so people can get your code, or if you want to have an easy access for people to use it without any technical hassles, make a web server and people can just run your method and play around with it. And that's it. Thank you very much.